Hello everyone and welcome to our section on 12.5 entitled Tree Diagrams. We're not just going to be talking about tree diagrams today, but how tree diagrams can help us solve some more difficult probability problems. So the first thing we want to talk about is the counting principle. It's used to determine the number of possible outcomes of a multifaceted experiment, also sometimes called a compound experiment. And it says if a first experiment can be performed in m distinct ways, meaning there's m choices in a first experiment, and a second experiment can be performed in n distinct ways, so it can have n possibilities, then the two experiments in that specific order can be performed in m times n distinct ways. Getting ready in the morning sure can be a hassle. Let me show you what I mean.
Wake up in the morning feeling like P. Diddy.
Hey, what up,
Grab
girl?
my glasses, I'm out the door. I'm gonna hit this city.
Let's go.
Before I leave, brush my teeth with a bottle of Jack. Cause when I leave for the night, I ain't coming back. I'm talking pedicure on our toes.
So here we have 3 red Lancer shirts, 2 pairs of jeans, and 4 pairs of shoes. So let's see how many different outfits I can make out of these.
Don't stop, make it pop. DJ, blow my speakers up tonight. I'ma fight till we see the sunlight. Tick tock on the clock, but the party don't stop. No. Don't stop, make it pop. DJ, blow my speakers up tonight. I'ma fight till we see the sunlight. Tick tock on the clock, but the party don't stop. No.
So in example 1, it says find the number of possible outcomes when a die is rolled and a coin is flipped. So the die right here has 6 different ways that it can land. And the coin has 2, heads or tails. So if we want to find the number of possible outcomes when we roll the die and flip the coin, we basically multiply the 2 together. And so it turns out there are 12 possible outcomes for this experiment. Now for probability problems, it's often very useful to find a sample space of the experiment. And a sample space is a list of all possible outcomes. And a sample point is one of the possible outcomes. And so this is where a tree diagram can be useful and help us determine that sample space. So what you do is just pick one of the experiments. So I'll just pick the coin. Now the coin has 2 possibilities, heads and tails, and you write them both out. Okay, we got to think, we're going to roll a die and it's going to have its 6 possibilities. Okay, so a die has the numbers 1 through 6. So you can flip a coin and get a heads and then roll a die and get the numbers 1 through 6. Or if you had gotten a tails, you can still get the numbers 1 through 6 on the die. And so the tree diagram basically just points to all the pathways that can be taken in this experiment. Okay, so you start off with 1, and then off of each one branches off the possibilities for the other experiment. Now, listing the sample space is going to be basically just following each of these arrows, H1, H2, H3, so on and so forth. And so here is the overall sample space, and you'll notice that we have 12 possible outcomes. Now what this is useful for is finding some probabilities. So it says find the probability of getting a 3 or a tails in this experiment. So here's your sample space again, and we look. Well, the word or means the presence of 3 or presence of a tails is going to be part of our event. So we can see here's a 3, here's a 3, and then all the tails also satisfy our event. And notice this one right here has both. And the ones that have both are only going to get counted one time though. Okay, so there you can see the 3 and the tails. And so we get a total of 7 that satisfy your event out of 12. Now the next question says find the probability of getting a 3 and a tails. So now if we look at our sample space, which sample point has both a 3 and a tails? Well, it's just going to be this one right here. Okay, and so we need the number of sample points that satisfy the event, which is 1 out of the total number, which is 12. So here you can see how we can use in conjunction the tree diagram, which is going to help us get a sample space, and the fundamental counting principle, which is going to help us get the total number on the bottom. So example 1 dealt with 2 separate experiments, and they were completely independent of each other. Now in example 2, we're going to talk about a dependent situation. So it says 2 balls are to be selected without replacement, meaning once one is selected, it doesn't get put back in, from a bag that contains 1 red, 1 blue, 1 green, and 1 orange ball. So this idea of replacement is going to be important whether it's a dependent event or not. So this one is without replacement. Okay, so we're going to put our balls in the bag. And first we want to use the counting principle to determine the number of points in the sample space. So here's our bag, and you can see we have the 4 balls in it. And so the number of balls in the first draw, or the first experiment, is going to be 4. But then we choose one of the balls out, and we don't replace it. So now the number of balls in the second draw is down to 3, so it just decreases by 1. And so what we can do is just multiply these two together, 4 times 3, and get 12 points in our sample space. Okay, so when you have dependent events, okay, you're going to have to rethink the experiment after each time the experiment is run. So let's construct a tree diagram and list the sample space. So now in draw 1 we have these 4 options: red, blue, green, and orange. So then in draw 2, if we had chosen red, we would only have blue, green, and orange left to pick from. So you can see the 3 choices here after we chose red. If we chose blue, then we would have red, green, and orange left as possibilities. If we had chosen green, then we would have red, blue, and orange. And if we had chosen orange in our first draw, we would still have red, blue, and green left for our second draw. So if we just follow each of these arrows, we're going to get our total sample space. Okay, so red, blue, red, orange, red, green, okay, so on and so forth. And you can see here we do get our 12 sample points, and we can also see why it's going to be 4 times 3, okay, because each one of these 4 has 3 choices after it. So let's take the sample space and answer some questions now. So it says find the probability that 1 red ball is selected. So when we look at our sample space, we find all the sample points where exactly 1 red ball is selected, and so I see 6 here, so it's going to be 6 out of 12, or 50%. The next one says find the probability that a green ball is followed by a red ball is selected. So a green ball followed by a red ball. So here we chose a green ball first, and it's followed by a red ball, and that only happens 1 time, and so that's going to be 1 out of 12, which is about 8.3%. All right, let's move on. In example 3, it says you need to get from LA to New York as cheaply as possible. Layovers are usually the cheapest flights you can get. You find there are 2 flights from LA to Chicago, 3 flights from Chicago to Cleveland, and 2 flights from Cleveland to New York. So basically we're trying to get from LA to New York. When we look at this, from LA to Chicago we have 2 flights, or 2 possibilities. From Chicago to Cleveland we have 3  'Flights. And then from Cleveland to New York we have 2 flights. So this is our first example where we have 3 experiments happening all at the same time. Okay, it says use the counting principle to determine the number of different routes from LA to New York. Well, remember there were 2 flights from LA to Chicago, 3 flights from Chicago to Cleveland, and then 2 flights from Cleveland to New York. So the fundamental counting principle says we just take the number of possibilities for each experiment and multiply them together to get the number of different routes. So here we would just do 2 times 3 times 2, which is 12. So here we can see all of our different pathways, and it says use a tree diagram to determine the routes. And so what I've done is I've labeled the routes with letters. So the 2 routes from LA to Chicago are A and B, the 3 from Chicago to Cleveland are C, D, and E, and then the 2 from Cleveland to New York we can let be F and G. So we just start off with flight 1, which would be A and B, and then branching off of that we have our second flight, which could be C, D, or E, and that can be in both of the situations. And then branching off from that, it would be flight 3. So whichever pathway you're on, if you go to A to C, then you could still take F or G. Notice if you went B to C, you could still take F or G. And so this tree has 2 sets of branches. And if we look at the sample space, it's created by following each pathway of arrows. So A to C to F becomes our first one. And then A to C to G becomes our second one. Well, and that's all the ones that start AC. So we move on, go AD to F. So ADF, and then ADG, AEF, AEG, BCF, BCG, BDF, BDG, BEF, and finally BEG. And you can see our 12 sample points here. So if a route from LA to New York is selected at random and all routes are considered equally as likely, find the probability that both routes A and G are used. So this is an important concept here of equally likely events. Because if any one of these flights is more likely than the other to be chosen, then this probability doesn't make any sense. Okay, so we have to think that each outcome is equally as likely. So we want to know, are routes A and G used? Okay, so it has to use both of them. So it's not in this one, but A and G are both used here. It's not in this one, but A and G are both used here. It's not in this one. A and G are both used here. It's not in this one, not in this one. None of these have A in it. So it looks like our total is going to be 3 out of the 12. Now find the probability that neither routes D nor F are used. So we don't want either D or F. Okay, so anything with a D we're going to cross out. Anything with an F we're going to cross out. So not there, not there. Can't have the D. Can't have the F. Can't have the F. Can't have the D or the F. No D's. And no F's. So what we're left with here is 1, 2, 3, 4. So this one's going to be 4 out of 12, or 1/3. Alright, so that is how we can use tree diagrams to help us find a sample space and how it relates to the fundamental counting principle, all helping us to find probabilities.